بسم الله الرحمن الرحيم. بنرحب فيكم في محاضرة رقم 10 في ال Random Variables and Stochastic Processes. اليوم يمكن المحاضرة الماضية محاضرة رقم 9 تكلمنا عن Transformation of one Random Variable، لكن أخذنا حالة خاصة اللي هي المونوتونيك Functions. اليوم رح نتكلم على لو كان الفانكشن Non-monotonic شو بدنا نسوي. أوكي. Non-monotonic transformations of continuous random variable. اوكي، اذا الفانكشن الموجود عندنا هون راح يكون non monotonic، بمعنى انه it's not one to one anymore. يعني ممكن يكون في عندي function one single y coming from more than one x، يعني x1 and x2 goes to the same y. مثلا زي الاكس تربيع، يعني انا بتكلم عن الاكس تربيع انه if you have a function like this then you have x1 and x2 going to the same y. So this is, we call it a non-monotonic. No, it's not monotonic anymore. There is no one-to-one correspondence, and we have to deal with such functions. So the fundamental theorem here to find fy of y for a specific y. We solve the equation. So we solve the equation y equals g of x. Okay. Denoting its real roots by x sub n. Okay, so we have y equals x of x1 equals x of x sub n as many roots as we have. So if you have a second order equation, let's say you have something like this, let's say that you have y equals some constant times x squared, then you can say that, okay, x squared equals y over c, and x1 and 2 equals plus minus square root of y over c. Okay, so you have two roots for this equation, x's in terms of y. Okay, so we have this as a y, then fy of y, so this is the result that we are looking for. It's equal to fx of x1 over the magnitude of g prime of x1 plus fx of x2 over the magnitude of g prime of x2 plus fx of x sub n over g prime of x sub n, etc., where g prime of x is the derivative of g of x. Okay, so this is our transformation, non-monotonic transformation, y equals g of x. And we would like to find what will be fy of y based on this transformation. Okay, so to see the proof here for this result that we have here, the proof, so without loss of generality, we assume that the equation y equal g of x has 3 roots as shown. Okay, so we'll assume that we have 3 roots, and this will go for more than that or less than that, it's the same. Okay, I'm gonna draw the function g of x. So you have, this is the function g of x, and we will draw the probability function. Here, this is x, and this one is also x. So this one is f(x) of x. This is the density function of x. And this is our transformation, y g of x. Okay? Now I'm going to assume that you have one y, and this y coming from 3 x's, x1, x2. So you have function. This is y equals g of x. It has 3 roots, 1, 2, 3. For every y, you have 3 x's, and this is the third one. So this is x3. Okay? And I'm gonna say that if I move this y to y plus delta y, so if you move by an infinitesimal length of y up in this direction, then you will have for x1 to be moved in this direction. So this is delta x1, and you can see that this is the area underneath this one here. Now if you move delta y from this one up to here, so x2 moves here, so it goes down because of the negative slope of y, so it goes, this is x2, goes in this direction, delta x2, and the last one is goes in this direction, delta x3, so it moves further to this. So you have 3 areas coming from by increasing this. So what I will try to do is find what will be fy of y times delta y, or dy. So I can assume that fy of y times dy, this is equals to the probability that y is between y less than or equal y plus delta y. So fy of y times dy is equal to the probability between y and y plus delta y, this infinitesimal length of y. Okay. Okay, this one here, the probability of y less than or equal y less than or equal y plus delta y actually corresponds to three periods in x. So this is actually coming from the probability that x greater than x1 less than or equal x1 plus delta x1 plus the probability that x greater than x2 plus delta x2, because delta x2 is negative, less than or equal x2, plus the third one is the probability that x is greater than x3 less than or equal x3 plus delta x3. So you have, for one change in y, you have three changes in x. So you have three periods, three probabilities. You have to sum them up because they are disjoint and find their probabilities. Now, I'm going to take the first one here, the first period. This one here, probability of x greater than x1 less than equal x1 plus delta x1. This is equals to f of x1 times dx1. So this is the length is dx1. The amplitude here will take it from x1, will not take the second plus delta of x. So f of x1 times dx1. Okay, and this is equals to, if you go up here, you can see that this dx1 is the same as here. So this one is dx1, and here is delta y, okay, or dy. So dx1 is equal to the slope g prime of x, okay, or dy divided by g. So dx1, f of x1, and dx1 is equal to dy divided by g prime at x1. So the slope here is g prime of x1, which is equal dy over dx1. If you divide them, then you will have dx1 to be dy over g prime of x1. If you take the second one, probability of x greater than x2 plus dx2 less than or equal x2, this is equals to f of x2 times the absolute value of dx2, because dx2 is negative and the probability is positive, so you have to multiply. We are taking this as a distance, not as a يعني مش إزاحة خلينا نحكي. So this is a distance, not okay. But so it's a distance. So we take the absolute value. We need to find the area here. So this area is f of x2 times dx2. But dx2 is equal to dy over g prime of x2. Okay? Which is, this here is delta x2. This here is delta y dy, and this is the slope of g prime of x2. Okay. All right, so this is dx2, and the last one, probability of x greater than x3 less than or equal x3 plus delta x3, and this is equals to f of x3 times d of x3. And as I said here, the displacement here, it's not the displacement, it's a distance. So the distance is delta x3 multiplied by the amplitude. يعني طول في العرض نضربهم في بعض وبيعطيني انه هذه الفاليو و dx3 is equal to dy divided by g prime of x3. If we take those three or those results that we have here, substitute for dx1 what is it equal in terms of dy over g prime of x1, and those here, you will end up with the result that we have in our theorem. So the theorem will apply, and we can say that fyy dy is equal to fx of x1 over g prime of x1 absolute times dy plus fx of x2 times dy over g prime of x2 plus the third one fx of x3 dy times g prime of x3 absolute. So dy, and with dy here, and we end up with our function. Notice that we have here the absolute, we don't have here absolute, but this one is positive, this one is positive. Why do we have the absolute value? We have the absolute value because, first of all, distance here is going to the negative side, but the g prime is also negative, so you have two negatives together. This is why you will have the absolute value, and you sum the resultant with absolutes. Okay, how can we apply this? Let's take the example. Let x be uniform random variable defined over the interval between -5 and 5 if y equals g of x equals x squared. Find fyy. Okay, so this is an example. X squared is a non-monotonic function. I will always advise you to draw the function, to draw the random variable and the function beneath each other and see how things looks like. So you have, this is our x squared, and we have underneath is a random variable between -5 and 5. So this is a uniform random variable, and this is fx of x, okay? The amplitude of this one is 1/10, so it's 0.1, as we know for the uniform random variable, so it's 0.1. To see, this is x, and this is our y, which is equal to g of x. And as we see, it's a non-monotonic function because we have, for every value of x, we have two values. Sorry, for every value of y, we have two values of x. And we can see that from -5 and 5, both will go to 25. And so this is your range of y. Actually, your range of y will be between 0 here and 25 here. So will be 0, 25. So this is our range of y. And it's very important to keep this in mind. Okay? Okay. Now, to start, this is part of the solution actually, to decide what is the region of y that we are looking for. Okay, so this is our region of y. Now, how many solutions for x in terms of y? We have two solutions. If you put y equals x squared, then you have x1 and 2 equals to plus and minus square root of y. So you have x1 equals minus the square root of y, and x2 equals plus the square root of y. So you have two solutions. Okay. We also need to find g prime of x, which is equal to dy by dx, and this is equals to 2x. Okay. So g prime of x1 equals minus 2 square root of y, and g prime of x2 equals plus 2 times the square root of y. Okay? If we do this, then we are almost there. Then fy of y equals to fx of x1 over the magnitude of g prime of x1 plus fx of x2, g prime of x2, and this is equals to, how much is fx at this x1? Okay, it's 0.1. It's a constant value divided, so for each x you substitute x1 in terms of y. So this is 0.1 divided by minus absolute plus another 0.1 divided by 2 square root of y, and this is equals to 0.1 over square root of y, 0.1 y to the minus 1/2. Okay. So the solution of fy of y is equal to this for y between 0 and 25 and 0 otherwise. Okay, just to check your solution, we can check our solution by finding the area under the curve of the new PDF. So if you apply fy of y dy from minus infinity to infinity, this should equal to 1. So the integration from 0 to 25, 0.1 y to the minus 1/2 dy is equal to 0.1 times y to the power 1/2 times 2 times 2, and this is applied from 0 to 25, so this is equals to 0.2 times 25 under the square root minus 0, and this is equals to 0.2 times 5, and this is equal to 1. So we did things in the right order, and we find the new PDF for fy of y based on our transformation. Okay, let me point here. What if we have a discrete transformation? We have discrete random variable, sorry. We have transformation. So if you have a transformation of a discrete random variable, so we have x is discrete random variable while y equals t of x or g of x is a continuous transformation or function. Okay, so if we have this, we can if we have f of x, we took it before, it's the summation over n p of xn times delta of x minus x sub n. So it's impulses with the probability of each x at that weighted deltas with the probability of that x at that particular delta, and the distribution is equal to the summation p of x of n u of x minus x sub n. If we do the transformation, then fy of y is equal also to the summation p of yn delta of y minus yn over n, and the distribution also is equal to the same summation over the same n p of yn times u of y minus yn, where yn is the transformation of xn and the probability of yn, where y sub n is equal t of x sub n, and probability of y sub n is equal to the probability of x sub n. It takes the same probability. Of course, this procedure is valid for monotonic and non-monotonic transformation. Transformations. Okay. Let's see an example. If you have an example, we have x's to be -1, 0, 1, and 2, with their probabilities. Probability of x equals, for this one, to be 0.1, 0.3, 0.4, and 0.2. So you can say that let's put them in table. I think it will be much better to see them in table. Okay, so we have this. So we have x, we have 4 values. Their probabilities are given here in this function. P of x, for each x, you have its probability 0.1 plus 0.3, 0.4, 0.48, 0.8, and 0.2, it's 1. Let's define y equals t of x equals 2 minus x squared plus x cubed over 3. So this is our transformation. I'm going to put the transformation up here so that, let me just put it here, because things will be more clear. So t of x y, which is equal to e of x, is equal to 2 minus x squared plus x cubed over 3. We need here to find the density function, fy of y. Okay. Well, if we continue the table, I'm gonna find y, which is equal t of x, and if we apply this here, x equals -1, so you have 2 minus 1, 1, plus -1/3, so you have 2/3 here, Okay, you have 0, so 0, 0, it's 2. You have 4 over 3, and you have here 2/3. And you can see that this x and this x goes to the same y, so this is a non-monotonic transformation, because 2 x's goes to the same y. Now, because of that, okay, let's first do the probabilities. Probability of y, it's the same, 0.1, 0.3, 0.4, and 0.2. So you have those T of x and probability of y, and we can say that Fy of y is equal to 0.1 delta of y minus 2/3. And you have another 2/3 here, so it's plus 0.2 times delta of y minus 2/3 plus 4 over 3 delta of y minus 2, 4 over 3, sorry, I'm sorry, 0.4, sorry about this, 0.4 delta of y minus 4 over 3 plus the last one is 0.3 times delta of y minus 2. So those two are two deltas at the same location, so we can add them together. So we add their probabilities, and so this is 0.3 delta of y minus 2/3 plus 0.4 delta of y minus 4 over 3 plus 0.3 delta of y minus 2. You see, it's a very easy procedure to do the monotonic or the non-monotonic transformation of discrete random variables. You take the discrete values, you transform them, you take their probabilities, and they are the same as the probabilities of their corresponding y's, and you do the delta function. If you have the same y coming from different x's, then you have a non-monotonic, and you add those probabilities, this one and this one, to be at the same location, which is y equals 2/3, as we did here, the 0.1 and the 0.2. Okay? So with this, I think we covered the non-monotonic case, we covered the discrete random variable, whether it is monotonic or non-monotonic, and then we will move to next lecture and next subject that we need to cover. Next subject we will talk about the multiple random variables. Now, if you have not only x random variable, you have x and y and z, and you can extend this to as many as random variables as it takes, and we'll see it in next lecture. Thank you very much, and I hope you find this lecture interesting. Thanks.